All right, welcome ladies and gentlemen. This is video number 7, our final video for our redox and electrochemistry unit. You will need your notes open to page 35 for this, page 35. And in this I'm going to be talking about electrolysis and electrolytic cells. So, what is electrolysis? Electrolysis is a process process that will use energy to cause a decomposition to happen. Electrolysis reactions are almost always decompositions, but they're decompositions that would not occur on their own. That's what that non-spontaneous means. It will need energy of some sort in order to happen. Water can be decomposed through electrolysis. Water doesn't normally decompose on its own, which is a good thing. It's a good thing that water doesn't just spontaneously break down, but you can get it to break down through electrolysis. And very typically in electrolysis, the energy that's used to cause this process to happen is electricity, electrical energy. An electrolytic cell is simply a type of electrochemical cell. Remember, a voltaic cell is also a type of electrochemical cell that basically can carry out this electrolysis process. So it's a cell that will use electricity. Notice this is a big difference between voltaic cells. It will use electricity, it will use electrical energy to cause a non-spontaneous redox reaction to occur. So like all of those non-spontaneous reactions, when we think about table J and the activity series, and will this reaction occur or will it not occur? Well, if it's non-spontaneous, then it won't happen on its own, but if you use an electrolytic cell, that electrolytic cell can kind of force and push that reaction to happen and get that redox reaction to happen. So notice we do absolutely still have redox reactions, but in an electrolytic cell, but they're not reactions that would happen unless you are putting energy into the system. So this cell, this electrolytic cell, instead of creating electricity like a voltaic cell does, it needs it, it requires it, it uses electricity. This is just a picture of an electrolytic cell. Focus on the one on the left. Right now, I just want to point a couple things out. So this is an example of an electrolytic cell from industry. Notice that we're putting NaCl into the cell, and it looks kind of fancy, but you know it's an industrial cell. So we're putting NaCl in, so that's just salt, and we're getting out sodium and chlorine gas. So notice that is a decomposition reaction, and if we balance it, then we just need to do that in terms of getting the same number. Decomposition. This is the decomposition of sodium chloride. This doesn't happen on its own. That's a good thing. You do not want your table salt spontaneously turning into poisonous chlorine gas and explosive sodium metal. That would be bad. But if you're the warlord of a small country and you want to build up the amount of poisonous chlorine gas and explosive sodium metal that you have, you could run an electrolytic cell and put salt in and get this stuff out. Now on the right, this is much more the type of electrolytic cell that we're going to see pictures of. I want to point out a couple things about this. First of all, notice we still have anode and we still have a cathode and we still have a wire. And notice the electrons are still going through the wire from the anode to the cathode. So that is identical to a voltaic cell. Also notice that the anode is still where oxidation is occurring and the cathode is still where reduction is occurring. But we do have a big difference in that we have this battery here instead. And we don't expect to necessarily see a battery there. That's the difference from the voltaic cell. This is the battery. This battery is what is forcing the reaction to occur. It supplies the electricity. So that's what is getting this reaction to happen. So how does an electrolytic cell do this? How does simply this battery actually cause this non-spontaneous reaction to occur? I'm sorry, how does it differ? Excuse me, how does it differ? So first big way that voltaic cell differs from an electrolytic cell. Voltaic cell, we have a spontaneous redox reaction. it generates electricity. Versus this other type of cell, the electrolytic cell, it uses electricity in the form of the battery to force a non-spontaneous reaction to occur. So this one is electrical energy, sorry, chemical energy gets turned into electrical energy. That's a voltaic cell. Versus an electrolytic cell, electrical energy gets turned into chemical energy, in that it's using the electricity to force this chemistry reaction. Electrolysis of water. So this is the diagram on the bottom of page 35. How does a electrolytic cell get this reaction to occur? And the big thing that I want to point out about this is the charges on the battery, because hopefully you know that a battery has a positive side and a negative side. And the whole reason that this battery can force this reaction to occur, it has everything to do with these charges. If you want your electrons to move from the site of oxidation, i.e. the anode, again, we have the exact same, anode is always oxidation, to the cathode, which is reduction, always going to be reduction. In a non-spontaneous reaction, they won't do that on their own. The electrons will not move on their own from the site of oxidation to the site of reduction. But if you hook the positive end of the battery up to the anode, well, it's positive. And, you know, electrons are negative. And what happens when you put a positive next to a negative? Well, the negative will be attracted to the positive. So by putting the positive end of the battery next to the anode in an electrolytic cell, it is essentially pulling the electrons out of it, because the electrons will want to move to the positive charge, right? The electrons are pulled out of the anode. They're forced out. It's kind of like a vacuum sucking them out. And then the electrons, they get to the battery and they travel through the battery and they hit the other side of the battery, and you've hooked the negative end of the battery up to the cathode. You don't want the electrons to stay in the battery. You want them to go to the cathode, where they will reduce the cation that's there. But by putting the negative end of the battery next to the cathode, a negative and a negative will repel one another, right? That electron won't want to stay there. So that electron is going to get pushed into the cathode in order to force the reduction process to occur. So what we've done is we've switched the signs on the anode and the cathode in an electrolytic cell. And the reason we've done that is through the battery, in order to pull the electrons out of the anode, to force the oxidation process, losing electrons, and then to push them into the cathode to force the reduction process, i.e. force the gaining of electrons. So again, a big similarity between these cells, this is page 36, your oxidation will occur at the anode always, your reduction will occur at the cathode always. That is going to be identical between your voltaic and your electrolytic cells. But, massive difference, the signs on the anode and the cathode. The charges are reversed. So in an anode, in a voltaic cell, the anode is negative. In an electrolytic cell, the anode is positive. And then likewise for the cathode. In a voltaic cell, the cathode is positive, and in an electrolytic cell, the cathode is negative. And this goes along with the other difference in terms of spontaneity. Electrolysis and electroplating. Electroplating, this is our sort of final little bit. What is electroplating? It is when you can use, it's when you use an electrolytic cell, i.e. using that thing that has a battery in it, to coat objects with metals. If you have any plated jewelry, like silver plated jewelry or gold plated jewelry or platinum plated jewelry, where it's not that metal all the way through, it's just that metal on the outside, that was generated through electroplating. It was generated through this process. And this diagram here is showing an electroplating diagram for electroplating this spoon. So we have this spoon right here, and we want to plate it with silver. Well, the silver ions won't spontaneously coat the spoon. You put this spoon in a solution of silver ions, the silver ions will not just automatically turn into silver metal atoms on the outside of the spoon. But The battery will force the electrons to be pulled from the anode to the cathode, and it will by forcing the electrons in, the electrons will be forcibly combined with the silver ions to form a silver coating, which is shown in the half reactions right here. So the anode is oxidation. Notice that we actually have the same, we have silver metal here, and by forcing the oxidation to occur, notice that we have the silver metal getting turned into the silver ion right here. So we're forcing this oxidation, we're sort of generating this, right? We're making this. And then this is in solution. So that silver ion in solution, now, when the electrons come in, when they're pushed in from the battery, they're going to combine, right? This electron is going to combine with the silver ion in solution to create solid silver. And this is what's on the outside of the spoon. So that's plating the spoon with that silver metal. Whenever you're doing electroplating, the object that you want to plate has to be the cathode. Has to be the cathode. Because remember, I have an ox and a big red cat. Big red cat. The cathode gets bigger because you're generating solid atoms on the outside of it. So if you want to plate something with silver or gold, that has to be the cathode. It can't be the anode. The anode dissolves, it corrodes away. But the cathode will increase in mass, will increase in atoms. So your plating object has to be your cathode. All right, so we're going to practice with this. We're going to do a web lab with electrolysis, look at a demonstration when you come to class.